Today we're going to take a look at the V3 NexPower sodium prototype that I received earlier this afternoon. This is not it. First I wanted to talk about the engineering process because there seems to be some discord maybe on whether or not it's fair to evaluate prototype hardware. And I will say that if I had production hardware or even later prototype hardware, I would review it. But I don't because NexPower won't ship it to me. And I think that that does a disservice to the community, which is why I'm doing these reviews. So first I wanted to talk about the engineering process and where you might be at certain time periods. The reason this is important is that the NexPower prototype that I received was manufactured within the last 3 months. It's actually quite a bit less than that. I want to say it's probably 2.5 months. So it's not that old. So I pulled out the LIBCM product. This is a product I designed, and I have the 3 revisions of it. I have Rev A, Rev B, and Rev C, and I wanted to talk about the timeline here. So my Rev A, I ordered in 2021 of April. This never shipped. This was just kind of a can it work. If you look even, I have the connectors here hand soldered because we couldn't find the connector at the time. But if you'll notice, my Rev B hardware is mainly the same, and this was actually ordered 3 months later, 2021 June. So, April, May, June. It's only 2 months later. This was early April. This is, I think, mid-June. Doesn't matter. It's the same time frame here. If you notice, these are kind of similar. If you'll notice, not a lot of things have changed. Now, conceptually, there are certainly things that have changed. You can see I have this dead bug wire here. There were some noise issues. Some things changed, but the general primitive of the product has not changed. This connector got longer, but it's still there. And so this is about the time difference between the prototype NexPower that I have and now. So if we were going to be shipping in August, which was the original time frame that NexPower gave, that's kind of where we would expect this hardware to be. So if I point out things like, this is a 60S architecture, it's still a 60S architecture here, and it's still a 60S architecture here. Things haven't changed. Now, you will notice there's fans on here. These are just, I scavenged parts. These were way early in the process. I only ever made 1 of these, this one right here. I made 5 of these. This Rev B. The Rev C actually shipped, and they're still out. They've been out in the field for over 2 years. I've had a couple of RMAs. Some of them were user error. I think I've legit had 2 RMAs on the Rev C that weren't customer inflicted, damaged the board, etc. So these have been happily shipping now. So this was, I started this design in February of 2021, ordered in April, ordered a Rev B that I intended to ship in June, but found some issues with some of our isolation serial bus stuff. You can see I have some dead bugs here. Again, I'm not trying to get too much into the detail. I'm trying to show you where a product should be at certain points in the prototype cycle. This is 100% a prototype here. It did work. I mean, I drove this in my car. I just had to dead bug some things. You can see some dead bugs there. The Rev B, worked as well. Again, had some noise issues I had to do, and then that came to Rev C, which again shipped, so this was June, so July, August, September, 3 months later, shipped. So if this was the prototype there, here's the shipping. Again, this worked as well, as did this one with some dead bugs, and this one also with some dead bugs. This Rev C it was ordered in 2021 September, so 3 months later. But if you'll notice, it didn't ship for several more months. So October, November, December, January. It was 4 months after I ordered this PCB that I actually shipped these units, and that's because I had to validate the product. So if you're looking at a prototype 4 months out that you've received, you ordered and then you've received it, this is probably what we're looking at with the NexPower pack. So I just kind of wanted to show you that the design has not conceptually changed. You cannot change a design and mass produce it in 3 months. And again, the reason I'm stressing the 3 months is that this NexPower pack was assembled less than 3 months ago. So let's clear this off. This is just the show and tell. I know that certain members in the Toyota community don't care about my product, but I don't care about them, so whatever. So I'm gonna pull the pack here. This is 1/2 of it. And here is the other half of it. So this is a 2-module solution. I've of course taken this other one apart to analyze it. So let's get it oriented properly here. So this is kind of how it goes in the pack there. This isn't really installed. I'm going to set that aside. And in a second, I'm going to remove this module because we're only going to look at one. They're both essentially the same. There are some differences, but they're not terribly noteworthy from a design review perspective. So these guys have a circuit board here that we will look at in a moment. It's something like this, how it's attached underneath, so you can see there. We will look at that so you can see it. But yeah, that's basically it. There are 70 total cells, so 35 in each pack. You have the majority up on the top on this 2-layer here, and then you have a small cohort of, I guess it's 1, 2, 3, 4, 5, 6, 7 more cells on the bottom here. They're actually sticking out. Let's see if I can, I can't turn this upside down because the cells will actually fall out. One of my complaints is that there really is no mechanical support here except for the very bottom of the tray. Otherwise, it's just the tabs holding it and then the glue, but you can see that the glue is already separated here. Yeah, let's get this one pulled off and we'll look a little more at the mechanicals here, and then we will look at the electrical as well. That's what I'm mostly interested in, although there are some mechanical issues. So as I mentioned on the forum earlier, and Jack has already responded saying, this is an early prototype. When you take this cover off, I apologize, I don't know if it went on this way or the other way. I'd have to consult the pictures. It was either this way or that way. Again, I have the pictures so I can figure it out, but. So this is the service disconnect. This is where the fuse and the service disconnect connect. And this is, as I mentioned, entirely bypassed. There is literally nothing inside. This is exactly how I received this. It's ignored completely. And Jack mentioned that this was only in some early old units. This unit was shipped in May of 2024. It's even signed by Jack C. So this is a May 2024, it's V3.3. And so that's not that long ago, right? June, July, 2 months, 2.5 months, because it's the end of July now. So yeah, this is not, you can't change this design that fast. So anyway, that's my first complaint. Again, Jack has already addressed this. This is actually fixed in the shipping version. Jack posted a picture. I don't have any reason to doubt that that's not the case. I have some major issues though that you would ship this to even beta customers without telling them, oh hey, by the way, this is completely unfused. If anything goes wrong, something in your car besides a fuse is going to burn down. I don't want to beat a dead horse on that because again, Jack has fixed it, but if that's the stance you take to save a little bit of time, you absolutely need to make your customers aware of that. So notwithstanding the fuse issue, which is scary, the voltage issue that a customer who's assembling your pack and touches the HVDC positive and negative with the service disconnect removed might expect not to be shocked. In the previous signal soother video, there was a kind of a high impedance path that could do that. This is now super low impedance. I don't know. Again, I said I wasn't going to beat a dead horse over that. That's an interesting decision even on a beta phase. So as I mentioned online, you can see, we're switching gears here. Sorry, I'm just trying to skim through this. So as I mentioned online, these cells are just glued together. There is no mechanical support besides this glue and the battery tabs, which are actually soldered on. So soldering is, again, not something you do on battery cells. So you can see right here that this is soldered. I've inspected quite a few. There's no tab welding. There's no, it's solder. That's bad for cells. Also, I'll note that this pack does not run, this is not cell 2, this is cell 5. So this is 1 minus, 1 plus, and then it goes down to 2 minus, 2 plus, and then it goes down again to that one little module in the bottom, comes across, that's 3 plus on the very bottom, and then comes across, has 4 minus to 4 plus, and then 5 minus to 5 plus. And so this is separated with some Kapton tape. I don't like that, especially considering the amount of pressure. If you look at the wires, we'll talk about these wires more, but you can see there's actually quite a bit of force put on them externally. I'm not sure exactly from what, because I'm not terribly familiar with the system. But there is some kind of force being applied to these. And so that's pushing these cells together. And because there is no mechanical support in here, you can see that these cells are able to just kind of move around. There's nothing to secure them in place. And again, in the demo video, the product release video, when they were showing the V3 product announcement, they actually showed the mechanicals here, and you could, see the pore spacing for airflow. This is a very small channel. Some of the channels are actually touching. So like this guy right here is touching, even though there's glue here. And that poses another problem. This is 6+, which would mean 7 minus, and then 8, and then 9. So this is cell 10. So we are 36 volts higher between here. Well, not really. We'd be 33 volts higher from here to there, but we'd be 36 volts higher. No, it would, because this is the negative the whole way. These are big cells, sorry. So this is a 36 volt potential with essentially no spacing here. And the problem you run into is that if you wear through the heat shrink here, this isn't heat shrink, but it's just a wrapping that is typical on cells, then that could actually cause a super high current short. There's no fuses in here. So that could cause a short and could just cause the pack to totally melt down. We're talking thousands of amps, whatever the ultimate cell decay is on this. It would be like 36 volts divided by, I don't know, 100 milliohms. You're talking 500, 600 amps shorting that out. This cell would just stop existing. So anyway, yeah, it's interesting. I mean, again, there's quite a bit of movement that can happen inside of here because there's no mechanical support. There's no mechanical separation. So it's just a matter of time. You can see the glue has already broken here. So I have a major concern that these cells could short out by wear rubbing. Typically, you would want to have some kind of plastic grid, or in this case, you could place like a weave, almost like a honeycomb weave that would space these cells out. And if you look in here, you can see there's actually foam just stuffed in here. So there's actually room in here. You could actually spread all of these cells apart about 1 inch, probably a little more than 1 inch, maybe 1.25 inches. And that would give you more airflow, and it would also give you room for your honeycomb spacer there. Let me grab a sheet of paper and I can draw that. Again, I did not see this in their product release. So I'm going to draw the profile view here. I'm adding more spacing, and I'm only just going to draw 5 cells. You could basically add some kind of, a plastic spacer between these cells. It would, of course, need to have holes for airflow, or it could really just be, in maybe 1 or 2 locations. So you'd have one here that goes all the way across, one here that goes all the way across. That would guarantee these cells are separated. It would also give you a lot of mechanical support if you curved the geometry of this correctly. You could actually get in here and get smart and actually curve that to where the mechanical stuff is going to keep these cells from vibrating around. But of course, once you have a plastic layer between them, that's 50, 75 thou thick, it doesn't really matter if they vibrate around from the short circuit perspective. Of course, you don't want the bus bars breaking off, and that's all that's holding these in place, because this glue is not holding them in place. If anything, it's only just keeping them separate slightly. So you're talking about these bus bars at the end that could break off because they're soldered on. Maybe the production ones are actually tab welded. I don't know. I haven't seen that yet. If I could get the final hardware, I would do it. But I mean, look how much these cells move around. That's going to be a lot of vibration all the time, and I'm a bit concerned. So I characterized a cell, and because we decided as a community that computers are not to be trusted, I printed this out. Of course, I've made it on a computer. Here's the usable energy. So that's this area here. I posted this picture online. So if you look at here, all of the area under this curve here, so all of this is the actual amount of energy that's in the cell. But because of the Prius's voltage limits, this didn't print very well. This is 250 volts, and this was the 210 volt Vmin, Vmax. This is the usable energy. It's about 837 watt hours. It's very, very small. The pack itself was about 2200 watt hours, so we're basically doing 36 or 37% of the usable energy. I'm sorry, 36 or 37% of the total pack energy is actually usable in the Prius. And that has to do with, again, this very linear discharge curve. So this is a single cell discharged at 5 amps until it was empty, or actually 1.5 volts. So this line is using the right y-axis, and this is the accumulated watt hours, which is the left axis here. These are actually lined up so they have the same divisions, which is why the voltages are kind of wonky here. I think it was like, I don't know, 76 millivolts per division here. All of this data is available if you want it. Again, certainly a sodium cell. It's this very characteristic curve. And I wanted to reiterate that with lithium, it's very, very flat. So with lithium, your curve would be, we'll do lithium iron phosphate maybe. So 3.65 volts here, and then you're going to drop down like this, and then you're basically flat, and then you do something like that. So you have a much larger usable range, maybe like 70% with lithium iron phosphates. We don't have it here because of this sodium. Of course, I have not tested this in the Prius. I don't own a Prius. It's not my area of expertise, the actual Prius itself. However, electrical engineering is, so knowledge prevails as far as theoretical stuff here. Feel free to comment that theoretical is not empirical. That's fine. The next thing I did was I measured the cell voltages just on this blade here because I haven't opened the other one up. And I found that there were some pretty major deviations in the cell voltage. And we'll look at why that is. We are going to ignore this one for now, and we will come back to it. This is actually a separate issue. You might be able to see it in frame, but if not, I'll point it out here in a second. So we're getting a spread here. If you'll notice, this spread seems to be kind of periodic. It's actually the lowest cell of every module. So 4 and then high and then low, 4 and then high and then low, 4 and then high and then low. This just has to do with the circuit itself. So let's look at that circuit. I measured these by hand with a calibrated fluke meter, by the way. So anyway, if anyone wants to challenge that. So this is the BMS board. It is not a BMS board. It's not called a BMS board here, but I think that's the intent. It is functionally identical to the V1 hardware. It's slightly smaller, but it is the exact same circuit. It's at a slightly different voltage set point. I think it was 3.516 volt was the enable, and the disable is about 3.512. I don't think there's actually an hysteresis there. I think that's just some kind of latchback. When it turns on, there's a small voltage sag. So at 3.51 volts, we turn on the discharge resistor. This is a V1 board, and on this V1 board, the resistors are here, and there's no heatsink or anything, and they're bigger, so whatever, they worked fine. On the V3 hardware here, the resistors are on the back, and they're smaller. It's 33 ohms per channel, and they basically sync onto this heatsink here. This is an aluminum heatsink. I was initially concerned there might be some high voltage issues because, of course, these are going to be all hooked up to high voltage, but actually the clearance works out on this. It's actually, this works. There's enough spacing here with the stud spacing there to make sure that we're not going to compress and then have puncture through, because this is not, this elastomer is not a high voltage approved elastomer. You can see how easy it is to damage. You would need some kind of high voltage approved one if the spacing weren't there. So I had no issues with that. But of course, I have all of the issues from the V1 hardware. So rather than just rant over all of those issues again, I will just tell you these are functionally identical. Electrically, they are identical. The voltage set point is different because it's sodium instead. The boards are even the same between the left and right modules. It's just whether or not this connector is soldered here or there. This is either going to the signal, the OEM BSU, that measures the blade voltages there, and then this is an interconnect between the modules. So if this interconnect is here versus there is whether or not it's a left or a right module. Otherwise, they're identical. Let's see, this board is from March of 2024. So Jack's claim that it's very old hardware does one of two things. One, it discredits his previous claim that they've been working on the V3 for 9 months, or rather that they've had prototype units out for 9 months. So that I never thought that was the case. But if we are going to call March 28th of 2024, that's the order date for this PCB. So this PCB didn't arrive until April. Hopefully there was some kind of V&V performed on it, so maybe it went out at the end of April. In that case, that's not old. Again, Jack's claim in this video was that I have old hardware. I absolutely do not. So again, the pack I have was shipped in May, and this PCB was manufactured in, essentially, it had to have been manufactured in April because you couldn't have ordered it on March 28th and had it before April. So anyway, it's identical. So if you want to watch my V1 review, this is identical. There are no differences except for the voltage set point. So, I mean, between the V1 and the V2.8 PCBs I reviewed earlier, you know, I would prefer the V1, but they're insufficient. So that kind of explains why we have a little bit of variance here. These circuits are completely isolated. So just like before, completely isolated. There is no supervisory control. So if a circuit gets unhappy, it can't tell the system to stop. The only way the system will stop is if a cell gets super, super bad, and also the neighboring cells are either good or higher, you know, super bad in the same way. There is a case where one cell goes high and the other cells go low, and you never detect that in the OEM thing. Of course, this is not detecting anything like that. This is literally turning a switch on if the voltage is above 3.516 volts. It's turning the switch back off if it's below. That's the only balancing that can occur. So let's look at this 3.516 volts though. Let's go back to this picture here. Where is 3.516 volts on this graph? It's about here. So this actually, 3.51, that's a little higher. It's about there. And so that kind of corresponds to the VPAC max that I kind of just arbitrarily picked based on community feedback. This would actually mean that the pack capacity is actually smaller, probably by another about maybe 5 or 10%. So this would be around 750 watt hours, assuming you turn the car off, all of these circuits balanced and then turned off at 2.512 volts, and then you got in the car. You'd have about 750 watt hours of usable energy, which is even less than a third. So basically, you can only use a third of the power. I know I've already talked about that. But what I was trying to get at here is, what about all of this area here? So this is additional headroom in case these can't balance in time. So this additional headroom is different than the V1. So in the V1, we didn't balance, basically, again, it was a lithium iron phosphate, so it's different. But if we just look at this as a percentage of state of charge, we didn't start balancing essentially until 100% state of charge with the V1 lithium iron phosphate. Here we're doing it lower so that we have more headroom. Now, this is a error in logic to the maximum here. Because we have no supervisory control failsafe mechanism, there is no actual headroom here. Because what happens if one of your BMS circuits fails, which is exactly what has happened here. So if you look right here, this is one of the BMS wires. Is this in frame? It is. Okay, so this BMS wire was disconnected, but it was loosely disconnected. So when I first measured the voltage, I measured 3.115 volts. And on this other one, I measured 3.279 volts. And I was like, what the heck is going on? And I actually played around with this. I have it on film. I will upload it as a separate video in case you want to challenge what has actually happened here. I will point out that this sense lead is green. Oh, there's the heat shrink for it. So this heat shrink here, this is basically a really poor solder joint. And I wanted to point out that the heat shrink, the wire insulation here is green, and here it's blue. So my guess would be that we somehow messed up the BMS and we had to flip some wires around, and then we poorly soldered it. Now these wires are not out as I have them here. They actually come here right on the cells, and there is a single layer of Kapton tape that prevents the wire from touching that other cell. This does not measure the top cell, it measures this middle or bottom cell, depending on how you look at it here. So anyway, once I figured this out, that explains what's happened here. So the actual cell voltages here are what is shown here. This was just my first data here, and I was measuring a low voltage here because as I was measuring, you know, the 10 mega ohms of my DMM was basically making a large voltage drop across this very poor connection. Put that in my bucket bin. So what has happened is that this cell right here is the point that measures the voltage between these cells, and because it became disconnected, the balancing circuit does not work here. And so the balancing circuit that would power the logic on this does not work because it's not powered. And so because of that, when you charge the pack past here, we build up the headroom, and normally our discharge resistors, when the car was, or actually at any point in time, because these are always enabled, it would pull all of the cells back down. So let's say your cells get up to here somehow while you're driving because you're regenerating really hard, I don't know, whatever. When you turn the car back off, these go down. We know for sure that we are going into this region, and it's probably very small. It's probably just from here until there. So say, I don't know, 240 volts to 250 volts, a very small amount. But over time, every time you charge the pack, you know, if you're regenerating, the discharge circuitry is going to enable about right here. And then it's going to discharge all of the cells that were overcharged except for the ones that are broken here. So that's what's happening here. It's not because this is a prototype. So even though this is a prototype, you know, this wire came loose, this wire can always conceptually come loose. These are hand soldered onto the cells. They have terrible routing, you know, where they route across cells. That's, ooh, okay, not great. So all I'm saying is in a pack with 70 of these cells, you know, you have about maybe 80 or 90 wires here. Even if you have a 99% passing rate, your overall rate's maybe 70%. That'd be 99 raised to the, you know, 80, 90th power or whatever. I have a calculator, so we could do that. Let's just assume we're 99% good at this, and we have 85 connections. So we actually have a 50%, more than a 50% chance. We have a 57% chance of having a BMS lead failure there. And even if we increase this to, you know, 99.99% effectiveness, we still have a 1% risk of failure per pack that one of these cells is going to come disconnected. That's pretty high. Even if you go out to the 5 nines, at 5 nines, you only have 1 in 1,000. But we're not, that was 6 nines. At 6 nines, we're not getting out there. This is not a Six Sigma product by any means. The point I'm trying to get at here is that this system needs to be able to detect when a cell has become disconnected because, you know, in the production version, they're not going to be, hopefully, gosh, be hand soldered here. But you still have, the wires won't have splices in the middle. But they will be probably still soldered here, and even if they are tab welded, that would be a miracle, to be honest. If I see that, I'll be surprised. We have to account for when these fail. These things need to fail safe. This product does not fail safe. This product is unsafe. This is a SIL 2 product. If you don't know what that is, look up SIL 2, there's no space. And you will see that this product warrants supervisory control so that it fails safe when an unsafe condition occurs. This pack has only been installed in the customer car for about 6 weeks. And it's already developed this huge delta there. I actually jotted it down. This is a 144 milliamp hour delta. That's more than 1% of the total pack capacity, and it's about 3% of the usable pack capacity. So in 6 weeks, we have added a 3% usable amp hour offset. This was going to overcharge these cells. And of course, these sodium cells are much safer, but that doesn't mean that you can just disregard safety elements like being able to detect when this occurs. How do you detect when this occurs? Hold on, I'm getting a prop. You have a supervisory control system that can detect when these things occur and measure these things and tell you and disable the system when these occur. And it's quite a bit more hardware to do that. Even if you don't need fans or if you're not generating from the bus, this is wholly inadequate. This I'm kind of just out of words for it. I know I've already talked about that. So let's just go down the list here. We've talked about this. So I just wanted to say, if Jack's latest V3 hardware, again, this is not that old. This is a 2.5-month old prototype. But if his latest hardware is better, Jack should send it to me so I can review it. I don't think it's better. I don't think that you could iterate this into this in 3 months. That it's impossible. And that's kind of what I had said earlier when I was talking about how I don't think you could develop a safe product from scratch in the amount of time that since I departed from the project. I never actually worked on any NexPower product at all. I very briefly courted NexPower, and then my one meeting with Jack was a disaster because Jack does not take feedback well. Nor do I dish it lightly, especially when there are dangerous things, especially when you have thousands of customers using your hardware that should still be in alpha. I'm referring to the V2.5 or 2 or 1 or any of the older stuff. Honestly, there are more. I'm impressed that you could make a less safe product, especially using safer cells. The sodium cells are more fault tolerant, but if you dead short these things because there's inadequate spacing between them and they vibrate themselves together, cars vibrate a lot. You know, when you do shake table stuff, you're talking about like a 5G, 1 hour test flight on all 3 axes. This would not survive that. This would be shaken apart. You probably have broken cells. Now, fortunately, if you had one of the battery tabs break off here that's just soldered on, the car would detect that. So that would at least be a failure mode that you could detect. So anyway, when I did the math on here, and thank you for the person who corrected me, the 27 kilowatts that the Gen 3 Prius can do works out to about 105 watts per cell of heat being generated in these. And I talked about earlier just that this is not enough airflow. Simply that you've put big holes on the top and smaller but still large holes on the bottom. That's not enough if your air can't get through. Again, the foam is here to force the air to rise through here, but there is very little cross-sectional area in here. I would be surprised if this was more than, I'm gonna do a very small calculation here. So I'm just gonna say that on average we're 0.0625 inches, and then we're, 16 inches long. This is all back of the envelope, and then we have 1, 2, 3, 4, 5, 6 of those. I would be surprised if there were more than 6 square inches. My guess was going to be 4, so that's actually pretty close. I'd be surprised if there was more than 6 square inches of cross-sectional area through this entire area here. And again, if we say this is a 16 by, 14, that's 224 inches. So we have about 1/4% of airflow through here. Let's look at another cylindrical prop here, and I'm kind of just grabbing this. I don't know what state it's in. So this is a properly designed cylindrical solution. You can see that there are actually channels for every single cell here, and there's a fixed width between them. This channel is actually, I think there's 4 layers, 1, 2, 3, 4, yeah. So there are 4 layers throughout this pack where the cell is air guided. So we have about maybe a 1/4 inch gap there the whole way, and there's no way this can rattle and short out. That's how you properly do this, and this is similar to what I'm proposing the structure here be. And you could actually put this in the structure and then put all the cells in here, and then if you wanted to tab weld them together. I'm not a big fan of the tab welding. I really wish that those were still screwed together, because what happens when a cell fails? I guess Jack sends you another entire pack. So, the only good thing I can say about this prototype that I've reviewed here is that it doesn't have the signal soother. This is DIY, homemade battery for your electric bike class battery here. Let's look at another battery. I'm gonna just kind of grab what is this? I don't even know what this is. At one point I knew what this is. This is a cylindrical, I'm not in frame yet, I know. Here's a professionally done cylindrical pack. It has proper spacing that's enforced by this plastic channel here. I have no idea the size or the capacity of this. At some point I knew. This is just the first one I grabbed that was cylindrical. You can see that all the tabs here come over off the cells, and then they're welded onto the board. They're actually fused on a per thing here, so if something shorts out, this will fuse and open. That's neat. The build quality is just much, much better than this. And this is entirely something that a single person could design and manufacture. And I think you could do it pretty quickly, in maybe 6 months, individually. A single person could do that. So the 10-year claim or 9-year claim that NexPower is having, you can't count the time you've been manufacturing or manufacturing again for your RMA rate. That's 30%. You can't count that as part of the development time. As I mentioned previously, I went from a Rev A prototype to shipping in, I don't know, 10 months. So literally starting, well, if you go back all the way, I started this project in maybe the end of February. So certainly in 11 months, I shipped a product. I'm still shipping. I don't have a 30% RMA rate. It's closer to 0%, much closer. I think my real RMA rate would be well under 1%, although my customer inflicted RMA rate is probably about 1.5%. So that's this video. This is, again, unscripted. It's going to be unedited. Yeah, I don't... Oh, there's a back. Huh. We talked about the wires. Cell terminals, they're still soldered. We talked about that. These bus bars are still way too thin for 150 amps on that. That's interesting. Oh, the pack ESR, we talked about that. 470 milliohms is what I measured. I basically dumped 10 amps into the entire pack, and I measured 470 milliohms. So at 125 amps assist, we're talking 7.3 kilowatts, which is 105 watts generated inside of every single cell during that. It's not great. It's not great at all. Just for reference, the pack I sell that's lithium is closer to 50 milliohms, so it's 10 times less resistance. And so you're talking about the difference between 7.3 kilowatts and 730 watts. So you're talking about the difference between 105 or 10 watts per cell. And I've given every benefit of the doubt in this single point test, because the ESR is nonlinear. The more current you push through that, the faster that is going to ramp up because of heat and chemical losses and all that. Technically, ESR is only the, it doesn't matter. I'm not even going to get into that. I've given every benefit of the doubt here to NexPower for their thing. And NexPower, they were at least forthcoming that this is the standard version, whatever the hell that means. I still don't understand why this product exists, other than that it saves the installer time because they don't have to do the individual blades. Saving your installer time on a product like this is not worth the sacrifice. In my opinion, there is zero reason to get that. If you were for some reason going to get the NexPower V3 or the NexPower V3 GT, which is, I have not reviewed, it's not out. I don't know if anyone has that yet. I sure don't. This product does not have a market. If you're going to get it, in my opinion, I don't see why this was brought to market. Especially because the V3 GT is still blade-like, although using sodium cells. It's going to have better separation because it's probably using the same channels of the old plastic enclosure from the V2 blades or whatever, where every single cell is separate, because it's probably a pouch cell. I don't know anything about the V3 GT. Based on what NexPower has said, I don't understand why this product exists. I understand the stated reason is that it saves the installer time. Who cares? It's a worse product. So I'm really at a loss on that. I think I'm done reviewing these products because they're not good and they're not getting better. I would really hope to see this V3 be better in some way. And while the cell technology itself, which you'll notice I've made very few claims about the cell technology, part of that is that I need to get my customer his pack back undamaged so that he can continue to use it in his car if he so chooses or she so chooses to do that. The only comments I've made regarding this sodium are just the usable range is very small because of the nonlinearity. This may be a vastly superior cell. It probably is. I don't see how it could be worse than the previous lithium iron phosphate cells in the V2.X and previous NexPower packs. But again, if the V3 GT exists and it only is going to be a month later until it ships, I don't see why you put any effort into this completely different design. The other design is they already had. So, and then lastly, again, I was saying it a second ago, there's no improvement. There's no attempted improvement. I just wanted to point out one thing. So they've taken this modular unit here. They're measuring 5 channels per bank here, and they're still connecting 6 pins. So if you look here between 5+, we have this red wire that's sensing 5+, and then we have the black wire that's sensing 6-. So yeah, the black wire here is sensing 6-, this is 5+. That's the same thing you're measuring, and you're routing it twice. So you literally have about 15 to 20% more wires in here than you need because you've now put this all on one board. You could have a 6-pin here and then 5, 5, 5, 5, 5, 5. And so you'd save 1, 2, 3, 4, 5, 6 wires on there. And I'm not saying that that's a safety issue. It certainly isn't, but it's just indicative of the failure to understand what you are doing. And it's, yeah, I wish I had better things to say. You know, at some point, maybe I'll review like a Lambda Gen power supply or something. Those things are really well built, but yeah, thanks for watching. I wish I had better news. You know, not everyone, people think that I'm out to just destroy this company because I don't like Jack for some reason. That's not the case. This is an unsafe product. It hasn't even started going on sale. And again, it's a prototype, but you got to remember here, if there were things being changed to this, like, oh, magically we're going to have a whole new BMS in 1 month or 2 months, 2.5 months from when this is. Again, this was made in May of this year. It's July of this year. So there's no rabbit in the hat that's coming out that's fixing this. Now, I will say, this is well positioned with this unified thing to have this replaced with new electronics that give us the supervisory control. So people have complained that I don't provide guidance when I give all of this poor feedback. And that's because Jack is not paying me as a consultant, and that's kind of a joke. At this point, I would not consult. I've already mentioned that. We have a different understanding of engineering, I think. Let's see how we would make this better, and I'm just doing this on the fly here. So we have this board here. We could basically remove this board and just throw it away, and we could keep all of these connectors here. And this is the wire that goes out to the BSU. It plugs in right here, like that, in here, and then this routes out the top, and you plug it in the BSU. I didn't plug it in all the way. So we have all of the elements that we need now to actually be able to have supervisory control. So we could take and put the LTC 6804 or probably the 6811, it's a newer version. We could put this circuit on here. Each one of these is 12 circuits, and you could get this a little more dense. So this is 35 total. You could certainly fit 3 of these, so 1, 2, 3. You could fit that on this circuit board. It would be a tight fit. You'd have to probably go to smaller balancing resistors. But to be honest, here's my balancing resistor, and this balancing resistor is big, to be honest. Here's Jack's, which has quite a bit more. It's completely unnecessary, unless you're just trying to, you know, every man is an island, every cell is an island here, balance these cells as quickly as you can so that hopefully they're all balanced because the customer parked it above whatever the voltage was, 3.56 volts or whatever. That becomes unnecessary when you can actually measure all of the cells and then say, hey, look, the lowest cell I measured was X. I'm going to discharge all of these slower to X, whatever that is, and it doesn't matter that it takes longer. And then, of course, if anything goes wrong, you can tell the system that stuff goes wrong. So that's the only saving grace of this architecture compared to the V3GT architecture, which is the same as the V2.X, is that you could now man in the middle. This is effectively a man in the middle circuit. And you could literally take the circuit I'm designing right now for the LIBSU, and you could put that here. You could split it across the two boards, have an ISO SPI connection between the two, and you could actually have a safe electrical product that can alert the car when something goes wrong. So how do you alert? One of those things is that, hey, look, you're measuring all the voltages and one voltage goes bad. Well, now you can manually control all of these, say with like an isolated PWM gate driver or something. You could just short one of the pins out. It doesn't even matter. You could literally just short, blade 1 to blade 2. Not actually, you're not shorting them together, but you could tell the car that there's 0 volts or 1 volt across the blade, and the car would stop, regen, or assist. It'd be a very easy way. And yeah, it would take you 6 months probably to, this is an open source design. You can go on my GitHub and copy this completely. The firmware is open source. All of this is open source. You could cram all of that onto here. If you wanted to, you could even get rid of a lot of this stuff here. A lot of this is just for additional protection or whatever, or you could make this a 2-layer board. You could print on both sides. You already are. I don't generally like that, but you could have 2 boards on top of each other. There's a million ways you can skin this cat where you get 3. And in fact, here's what I would do. The LTC 6218, I think that's what it's 6818, whatever. It's an 18 channel module thing, so you'd only need 2 of them, and that would give you 36 channels, and you'd just leave 1 channel shorted, so you'd be measuring 18 on one and 17 on the other or whatever. And that would lower this footprint here. I think you go up to like a TQFP 100 or something. It doesn't matter. You could maybe it's a TQFP 64. Again, the specifics of that don't matter. All of my firmware open source, so just copy that, put it on here, and make this safe. Now that doesn't solve your mechanical issue here, but you can again solve that with the spacer I mentioned here. And now you have a system that's probably safe, depending on how you design it. You've got your mechanical spacer here. You certainly need to move these leads differently to where the leads that are going lower are not, there's a couple of gussyings that need to happen here, but be my guest. Please properly attribute it if you do that, but you could take the last years of my life that's open source and put this into your product and make this safe in your 3.1 or 3.2 or whenever you decide to do it. This will work perfectly with the different sodium chemistry. No worries there. Yeah, that's how you could make this better. That would be this. And maybe when LIBCU is existing as I intend it with lithium batteries, maybe I could make a drop in here. I wouldn't be doing that for Jack. I'd be doing that for Jack's customers. So anyway, I'm sure this video is very, very long. I'm not going to edit it. Wow, 48 minutes. Awesome. It's about 10 minutes longer than I thought I'd do it in, but that's how it goes. As always, thank you for watching. Yeah. And if you have feedback that's constructive, I'd love to hear it. If it's not constructive, I'm probably going to poke fun at you and then eventually stop replying to you. Please talk to Azusa Prius if you would like to understand how that process works. Have a good day.